Hello and welcome to my channel. In the previous videos, we talked about how to calculate the support reactions in a simply supported beam. I hope you see them. I'll leave the addresses at the description box. In this video, we are going to learn how to draw shear force and bending moment diagrams. By drawing these diagrams, we can determine where the shear and the moment are maximum or minimum and how they vary across the beam. As you see here, we have a simply supported beam with a span of 8 meters. We have here at point A a pin support and a roller support at point B. And we have two kinds of external load, a uniformly disturbed load acting between the points A and C, and a point load in point D. So the first step we will do is to draw the free body diagram. As we learned, we have to draw the beam and locate the external loads and determine the support reactions. So here at point A, I will assume that YA is in the positive direction of Y and XA is at the positive direction of X. Here at point B, we have a roller support, so we have just a reaction at a direction Y. The external load we have here, point load, and we have this uniformly disturbed load. We have to convert this uniformly disturbed load into a point load. And we learned that we just have to find the area of this disturbed load. So it's 2.4. And it's always located halfway between the ends of the rectangular. So it's right here, 2 meters away from point A. I'll start by calculating the support reactions. We should use the static equilibriums. I'll start with the sum of the moment about point A equals to 0, assuming that the positive moment is the counterclockwise. So we have minus 8 multiplied by 2, which is this converted disturbed load. This 8 makes the beam goes clockwise, so the moment is negative. We have also minus 5 multiplied by 6, minus because 5 makes the beam goes clockwise, so the moment is negative, and 6 is the perpendicular distance between the point A and the point load. Then we will write plus YB multiplied by 8 equals to 0. The moment of B is positive because I will isolate YB. We have 8 times 2 plus 5 times 6 over 8. Using the calculator, we can find YB equals to 5.75 kilonewton. Now to find YA, the sum of the forces at the Y direction equals to 0, and this is the positive Y direction. So we have YA minus 8 minus 5 plus 5.75, which is YB. Using the calculator, we find that YA equals to 7.25. There is no forces acting at the X direction, So we write the sum of the forces at the x direction equals to 0, and this is the positive direction of x, so xa equals to 0. Now that we found the support reaction, we can start drawing the shear diagram. We'll divide the study into sections. We'll study every segment individually. As you see, we have AC, CD, and DB. To draw the shear diagram, you have to know the value of the shear at the first of the segment and at the end of the segment and the shape of the line in between. I'll start with the first section, AC. As you see, between A and C, X is between 0 and 4. We will write the equation of the shear in this section. We imagine that we cut the beam in some point between A and C, and we will write the sum of the shear in this point. So if we cut this section in some point, then the shear would be YA, which is 7.25 minus 2 multiplied by x. Now when x equals to 0, then shear equals to 7.25, which is the value of the support reaction. At the end of the segment, x equals to 4. Then shear equals to 7.25 minus 8, which is minus 0.75. We will draw while studying the segments. I think it's an easy way. The value of the shear force here is the same of the support reaction, 7.25. At point C, when x equals to 4, shear is minus 0.75. 0.75. And because this disturbed load is in a rectangular shape, so we are going to draw a line in between the segment CD. X at this segment is between 4 and 6. We know already that when x equals to 4, then shear equals to minus 0.75. Between C and D, there is no forces acting, so the shear will stay still. When we reach point D, there is a shear force acting at the negative y direction. So when x equals to 6, shear became minus 0.75 plus minus 5, which is minus 5.75. So we will draw immediately. Between C and D, shear stay the same. Then at point D, shear 5.75. Between D and B, there is no shear forces acting until we reach B, where the support reaction will close this shear diagram. So we close the shear diagram. After drawing the shear diagram, we can see that shear at this point equals to 0. We have to determine exactly this destination. because when shear equals to 0, the moment would be maximum. At section AC, shear were 7.25 minus 2 multiplied by x. Then we will write this equation equals to 0. And find that x equals 3.625. We have to find the moment in a significant point. I'll start step by step. At point A, moment equals to 0. At point C, the moment is 7.25 multiplied by 4, and the moment is positive because we are studying from the left, and YA goes clockwise, and when we study from the left, the positive moment is the moment that goes clockwise. Then we have minus 8 times 2. So the moment is 13. At point C, we have 13. At point D, we imagine that we made a cut, and we will look at the forces at the left direction. We have YA, which is 6 meters away from point D, and we have this 8 kilonewton, which is 4 meters from point D. So at point D, we have 7.25 multiplied by 6, the perpendicular distance between point A and D, and this 8 multiplied by 4. YA goes clockwise, while this 8 goes counterclockwise. So the value of the moment is 11.5. And the value of the moment at point B equals to 0. I left the maximum moment to the end. We imagine that we made a cut at this destination. So we have this uniformly disturbed load acting on this destination. So the sum of the moment about this point will be YA, which is 7.25, multiplied by the perpendicular distance between YA and F, and it's a positive moment. And this uniformly disturbed load will be converted into a point load by doing this: 2 multiplied by 3.625, which is 7.25, and it's located halfway between point A and F. So we will write minus 2 times 3.625, and by doing this we converted this uniformly disturbed load into a point load, times the half of this x. So the value of the moment would be 13.14. And now we completed the shear moment diagram. See you at the next video.